G'day everybody. In this lesson we're going to start looking at the binomial distribution. The binomial distribution is a particular type of discrete distribution which we dealt with in our previous lesson. In this lesson we'll talk about how we define a binomial distribution and how do we calculate those discrete probabilities once we've defined that distribution. Pascal's triangle is a mathematical object that has something to do with this distribution, and we'll find out what that is. And also I'm just going to touch very briefly on formulas for calculating the mean and the standard deviation of the binomial distribution. So as I've expressed here, when a random event has exactly two outcomes, success or failure, we represent the possible numbers of successes and their respective probabilities with the binomial distribution. So we'll break that down a little bit more in the next few slides. I'm going to use a few variables. It's important to understand what they are. When we talk about the number of trials in a binomial distribution, we use n to represent that quantity. The number of trials, or the trials themselves, are sometimes also referred to as Bernoulli trials, named after the mathematician Bernoulli. We'll talk about the probability of the success for one trial, and that carries a value that we use p for. And we're going to define the variable itself generally with x, but it doesn't have to be x, but we'll use x in this lesson. So the way that we define the distribution is we write down the name of the variable, x. We use this tilde, and we use bi to signify that this is a binomial distribution. And the two quantities that we use to define any binomial distribution is the number of trials, n, and the value of p, the probability of success. So just for a particular example, I'm using the TV show The Chase. In The Chase, there's one particular round where you go head to head with the genius. And so let's say, just hypothetically, that I generally guess 75% of the trivia questions in this show correctly. So I have a 75% success rate. In every head-to-head round, there are 7 questions. So this is a situation that we could use a binomial approximation, a binomial distribution. So we would recognize that the number of questions would be the number of trials. The probability that I get any one random question correct is 75%. Or as a value of probability, 0.75. And so I can say, right, this is a binomial distribution, and I'm going to write it in this way, using bi and using the values of n and p in brackets like that to define that distribution. So that's recognized notation for defining any binomial distribution. The binomial distribution can easily be represented with a tree diagram, particularly if the number of trials is fairly small. So in the first trial will either be successful or it will be a failure, and then given the result of the first trial, the second trial could also be a success or a failure, and so we get this ongoing probability tree. If I'm interested in how many successes I have in a certain number of trials, that's going to be a discrete quantity. And so really the binomial distribution is one type of discrete distribution, of which we already know the theory of. Here's some typical examples where we would use a binomial distribution and their values of p. Q is the complement of p. So for example, if I have a fair coin and I'm looking for how many heads I'll toss, the value for P in each of those trials is exactly 1/2. If we've got a die and I'm interested in how many times I'll roll a 6, in this case the value of P will be 1/6. The value of Q will be 5/6. If I'm doing a multiple choice quiz where there's 5 options and all I do is simply guess random options, the probability that I'll be successful if I'm randomly guessing will be 1/5, and so the probability of failure is 4/5. What's interesting, and we might talk about this in class, is how would we go about defining P and Q if we're interested in the probability that a randomly selected person is born in February. So here's a probability tree for 2 trials, and as you can see down the bottom, I've set up a probability distribution table. So the values of X are the number of successes. So we would like to show in this table how many different numbers of successes are possible here, and what's the probability of each of those outcomes. And so you can see it's possible that we could have no successes, where we fail twice in a row, and we would be multiplying Q by itself or squaring Q. That would be the probability of this outcome. We could have 2 successes, and likewise the probability of 2 successes would be P squared. There's 2 ways of having 1 success. We can succeed and then fail, or we could fail and then succeed. In each case, the probability of these individual outcomes would be P times Q. But because they both lead to 1 success, the probability that I'll succeed once in 2 trials would be 2 times PQ. And so this is our distribution, discrete distribution for the numbers of successes in 2 trials. Here we've got 3 trials. If you'd like to pause the video and complete that distribution table, that's not a bad idea. I'll pause it now. Okay, so here we're looking at the results of this discrete distribution. You'll see I've highlighted actually the result for 1 success. There are 3 different ways where I can have 1 success. The probability of each of those individual paths is P times Q squared, and so the probability of 1 success would be 3P Q squared. 0 successes would be Q cubed. 2 successes, 3P squared times Q, and P cubed for 3 successes. Here's just probability tree for 4 trials. You're welcome to try this one as well. Here we've got some results. I'm not going to go through all of them, but you can see there seems to be some sort of systematic way of going from one probability to the next. You'll notice that, for example, P is raised to the power of how many successes we're interested in, so P squared for 2 successes, P cubed for 3 successes, and so on. And there's also a bit of symmetry in these coefficients that we're using in front of each probability. So what about 5 trials? I actually don't want you to do this manually. What we're going to do is firstly think about it. We can see by the bottom row in the probability tree that there's a lot of outcomes with a probability of tree of this size, so we really don't want to go any bigger than this. But what you might have noticed, particularly for the 3 examples that we've looked at, is the coefficients and what's happening with those coefficients. So the coefficients for 2 trials were 1, 2, and then 1. For 3 trials, if you might remember, it was 1, 3, 3, and then 1. And then we had 5 coefficients for 4 trials. So the coefficient when we had 0 successes is 1. When we have 4 successes is 4. 1 success is 4. 2 successes, the coefficient is 6. 3 successes, coefficient is 4. And 4 successes, the coefficient was 1. What we're actually looking at here is Pascal's triangle. And if you're not sure what Pascal's triangle is, you'll see that there's a pattern from one layer of the triangle to the next, or one row, where the two numbers next to each other give us the number below. So 1 plus 2 is 3. Going from this row, 3 and 3 is 6, or 3 and 1 is 4. And the outside of each edge of the triangle is always 1. And so we can use this pattern without having to draw the probability tree for 5 trials. We can use this pattern to generate the coefficients for 5 trials. Remember, we'll need 6 coefficients because we need everything from 0 successes to 5 successes. So those coefficients will look like this. So we have 1, 5, 10, 10, 5, and then 1. We don't always need to look at Pascal's triangle. In actual fact, we actually only use Pascal's triangle usually when we don't have a calculator to use. These coefficients, being in Pascal's triangle, can also be generated as numbers of combinations. So you might remember from some combinatorics in Unit 1 and 2, 5C0 is 1, 5C1 is 5. And so we can see here, when we have 5 trials and 3 successes, we can use combinations to get each of those coefficients. So going back to our distribution table now, we can see the results of the discrete distribution for 5 trials. And there you can see our coefficients and the quantities P and Q used in each calculation. So let's summarise this. First of all, we are talking about using coefficients that are based upon combinations. So our general term for the coefficient is NCX, where N is the number of trials and X is the number of successes we're interested in. Using this notation for a binomial distribution, we have now a general formula for the probability of X successes. NCX, P to the power of X, and Q to the power of N minus X. A few general patterns to remember about combinations, and we might talk about these in class, but these combinations are true for any value of N. And a particular example, let's say we have a binomial distribution with 10 trials and a value of P which is 0.3, and we would like to know the probability of 4 successes. We now have a general formula that we can use to calculate that probability. First of all, we would note down the values of N and P, and the value of P, its complement, would give us the value of Q. And so we've got all of the values that we need and the formula. So the probability that X is equal to 4 would be 10C4, 0.3 to the power of 4, 0.7 to the power of 6. And eventually that gives us a rounded off answer of 0.2. You might want to pause the video at this point. There's 3 formulas that you might need to use for the mean, the variance, and the standard deviation of the binomial distribution. Okay, I realise I rushed this at the end of the lesson. We've talked about the binomial distribution and how we calculate discrete probabilities. We've seen how we use Pascal's triangle for coefficients, and we also have formulas for those probabilities, the mean and the standard deviation. If you have any questions, please write them down. and complete the Google form to log your attendance and check your understanding. Thanks very much.